Objective of this video is to introduce the input-output terminals of ExpEYES along with the graphical user interface. First of all, let us have a quick look at the input terminals and output terminals, and we'll come back to them one by one. All the black terminals here, they are ground terminals, that is our 0 volt reference. CCS is a 1 milliampere constant current source. PV1, PV2 are voltage sources. PV1 can be set from -5 to +5 and PV2 from -3.3 to +3.3. Square 1 and square 2 are square wave generators. The voltage changes between 0 and 5 volt and the frequency can be set anywhere from say 4 Hz to several hundred kilohertz. OD1 is a digital output that can be set to 0 volt or 5 volt. WG, the waveform generator, can generate sine wave or triangular wave with a frequency ranging from 5 Hz to 5 kHz. And WG bar is the inverted output of WG, but the difference is WG amplitude can be set to 3 volt, 1 volt or 80 millivolt, but WG bar is always 3 volts. Now coming to the input terminals, in1 is meant for measuring capacitance. You can connect a capacitor between ground and in1 and can be measured. In2 is for measuring the frequency of digital signals, and sen is a sensor input meant for measuring resistances. It can measure resistance from say 100 to 100 kilo ohms range, 100 ohms to 100 kilo ohms range. And A1, A2 are voltage measurement terminals, so they can measure the voltage and plot them as a function of time. The input to A1 and A2 can be from -16 volt to +16 volts. A3 is another input, but the input range is restricted to -3.3 volt to +3.3 volts. And there is an extra feature on A3. You can put a gain resistor here and amplify the signal. And the mic input, you can connect a condenser mic between these two terminals, and the output of the mic can be captured through software. Now let us try to use them one by one using the graphical user interface. So if you start the ExpEYES program, this is the GUI you will see, and you can start say from this school experiments menu some simple activities, say voltage measurement. So you can see there is a voltage, say help window has popped up. It says the connection you have to make is like this. So let us try to make this connection and see how to measure it. So let us make that connection. So we have a 3.3 volt battery here, so that we will connect between A1 and the other terminal to ground. So the battery is connected there. So let us come back to this one, and we want to measure A1. So here it is a 3.3 volts. So it is plus 3.3. If you reverse the terminals of the cell, you will find this as -3.3. So this is how you can do a simple voltage measurement. Now coming back to another one, suppose say let us do a capacitance measurement. So this is how you connect it. So we go back and make the capacitor connection. Say first of all we will connect a capacitor. It's an electrolytic capacitor, and let us connect this between in1 and ground. Come back to the GUI and measure capacitance. Big capacitance takes some time, so it's a 22 microfarad. So now let us remove that and use a smaller capacitor which we have made, say using two foils. You can see on a piece of paper there is aluminum foil on both sides, so it forms a parallel plate capacitor. So let us connect that between ground and in1. So we make these connections and go back to GUI and measure it. So it is in picofarads only, small capacitance. So we have made use of two features, and now let us go back to measuring resistance, a resistance measurement. So that you have to connect between the sensor input and ground. So let us do that. Again, have a look at this, and so between ground and the sen input we connected a resistance. So come back to it already. It says it is 992 ohms. It is reading it already here. So this is how you make very simple measurements using this. So now we have done some DC measurements, but let us go and try some AC measurements, direct and alternating currents. So here, so we can do a DC as well as AC. In the initial case we made the DC measurement by connecting an external button cell, but now what we will do is we have a DC source in this, that is our programmable voltage source. So let us connect PV1 to say A1, so we connect a wire from PV1 to A1, come to GUI, and A1 is 0, but using the slider or here we can set the PV1. So PV1 is 1 volt, you can see here it is reading 1 volt. If I change it to say -2, it is again changing here, right? Say if it is going to say -1, it changes. So whatever you set here, you read it back, or you can change it by using the slider. But you also notice that the A1 DC voltage is showing here, but it is also getting plotted as a function of time. That means if you have an AC voltage, we will be able to see the variation of the voltage with time. So what we can do is, instead of PV1, we can go and connect it to WG to explore the AC. So we connect it to WG. So you see here a sine wave is appearing, and this frequency we can change from the slider, and you can also decide what is the duration of the x-axis. Now it is total 2 milliseconds, so let us make it 5 milliseconds and set the frequency to say again 1 kilohertz. So in 5 milliseconds you find 5 cycles. And here, now if you look at this voltage measurement, it doesn't make any sense because it is instantaneous voltage. Every time it measures a different voltage, so there is no point in seeing this in this mode. So we come here for sine wave. If you enable this, it analyzes this data and say this is the voltage, peak voltage, and this is the frequency. So if you change the time base more, this measurement becomes a bit more accurate. That means more number of cycles, this measurement is 1 kilohertz and 3 volts. So now we can go and change the sine wave, say amplitude to 1 volt, and let us change the time base again, and we can come back and choose a triangular wave. So these are the features. Like, let's have a look at the sine wave amplitude once again. Suppose this 3 volt, I'm going to change it to 80 millivolts, so it becomes a very small signal. And if you look at our full scale is 4 volts, so this, seeing an 80 millivolt signal, we should not set a 4 volt full scale. We should go something smaller, right? So now the 0.5 volt full scale, it looks better. And now in this condition, if you make it 1 volt, you can see this input is clipped, So this 1 volt signal in a 0.5 volt range is not good, so we should go to a higher range. Or if you go to 3 volts, then we should choose appropriate voltage range. So this is how you change the voltage ranges. And now let us see how to see more channels. I mean, there is one output, so there is another input A2, so let us enable A2 also. So there is nothing connected to A2, so that's why it is showing like this. So what we'll do is we will connect another AC source, an external AC source, to this. Like this is our internal sine wave source. Now we will have another waveform that is from an external circuit as shown here. Here what you see is this is a small 555 IC oscillator, and it needs a 5 volt power, 5 volt DC and ground, and this green is the output. So we can power this unit to generate the AC signal. So let us take, say, the output, we will give it to A2, and this ground is connected to one of the ground terminals, and here we have a 5 volt